Okay, number 9 in 6.2 is another solid on a base problem. Here our base is a unit circle, x squared plus y squared is equal to 1, and that's as far as I need to read just to get started. My first graph over here on the left is two-dimensional, just the xy plane, and I'm going to draw the unit circle, which of course is centered at the origin with a radius of 1 right there. Gotcha. And what's going on now within that unit circle, guys? That's our concrete foundation. What are we building? The cross sections are running perpendicular to the x-axis. Now let's get used to it, guys. As soon as you see this phrase, perpendicular to the x-axis, that means that this is a dx problem here. So I'm going to draw a chord that runs perpendicular to the x-axis. Looks something like that. And that chord I just drew is going to be the base of a triangle, and a triangle whose height and base are equal. Okay, so I'm going to put a B right there for the base of that triangle. We need to come up with a way of measuring how tall or how long B is. And how do we do that? We're going to take its top function, what borders it above, minus what's on the bottom. So we need to take this equation of the unit circle, and because we're going to do this integral with respect to x, we need to solve this equation for y. So y squared is going to equal 1 minus x squared, and then we'll go and take the square root of both sides. Now remember, we forget this a lot. Every time you take a square root, there's got to be a plus or minus in front of that. So it's plus or minus the square root of 1 minus x squared. And the positive square root of 1 minus x squared, that's the top curve. The negative square root of 1 minus x squared, that's the bottom curve. So B is bordered by the square root of 1 minus x squared on the top minus the opposite. So of course that's going to make a plus the square root of 1 minus x squared on the bottom. Why did I switch to blue all of a sudden? So B then is going to be 2 times the square root of 1 minus x squared. Doesn't really look like we can simplify that any further than we need to. Now, you really don't need to draw what I'm about to, but over here on the right, the three-dimensional perspective, we've got our unit circle that's going to look something like that. Here in red is the base that we just drew, perpendicular to the x-axis and parallel to the y, and now they're telling you that this is a triangle whose height and base are equal. So what that means is that whatever b is for the length of your base, if I shoot this thing straight up in the air here, guys, we're going to go up the same amount there that the base was on the bottom there, okay? So we've got a triangle that looks like this. Now I should be clear with you guys, it doesn't really matter if your triangle looks like this or if your triangle looks like this, or if your triangle looks even weirder than that, like this. If all three of these triangles have a base of B, I didn't quite draw that one long enough, but okay, if they've all got the same base, and if they all have the same height, h, and your altitude here would take you outside, these three triangles all have the same area, even though this one's isosceles, this one looks like a right triangle, and this one looks like an obtuse scalene. If those three triangles have the same base and the same height, their areas are the same. So you'll notice I kind of drew this like that, like an isosceles triangle. I actually don't know that, but it doesn't matter. It doesn't matter if the triangle is leaning to one side or the other. So where were we, guys? Okay, that's what our cross sections are going to look like. So let's start off with something really, really simple. We need the area of a triangle here, and that formula is going to be 1/2 times its base times its height. But now, since this is a dx problem, we need to represent both base and height in terms of that variable x. Well, that's one of the things we accomplished right here. Area of your triangle, this will be as a function of x now, is 1/2 times a base of 2 times the square root of 1 minus x squared. So there's b, and now we need to multiply that by h. But what do we read here? The height of those triangles is equal to its base. So whatever we just put right here for base, we'll put the exact same thing again for its height. And I suppose, let me move that a little bit, we could clean that up just a little bit here. The 1/2 times the 2 times the 2, well, that cancels with that, and we get a 2. And then the root 1 minus x squared times another root 1 minus x squared just makes a quantity of 1 minus x squared. And it's tempting to distribute that 2. I'm actually not going to, and I think you'll see why in a second. So now that you've obtained your a of x formula, the rest of this should be relatively easy. Volume is going to be a definite integral. We said a long time ago that we were going to take this, here we go, that we were going to take this integral with respect to x. So I know a dx has to go at the end of that. Then let's take a look. I see a little mistake I made already. Oh well, I'll cram it in here. We're going to write this a of x function in for our integrand, but I'm going to put the 2 all the way out in front and just put the 1 minus x squared there as our integrand. Now the only thing I'm missing are the limits of integration, the lowest and highest values of x. So I go back here to this two-dimensional graph and say, okay, where did this region begin? Now we're talking x coordinates, so I'm reading it from left to right. This region begins right here at -1 and ends right here at +1. But since I think I'm going to do this one by hand, I'm actually going to take advantage of the fact that the base is symmetric with respect to the y-axis. I'm just going to integrate half of this, guys, from 0 to 1, but then double my value there. So that was the goof I realized a while ago. I should have left a little bit more space in front of that, but nothing we can't handle. All right, guys, so volume will then equal that 2 times 2 is going to make a 4 here. And now let's evaluate our antiderivative. So I'm going to put some brackets here. Antiderivative of 1 is an x, and the x squared becomes a 1/3 x cubed. Close off the brackets, 0 on the bottom and 1 on the top. Okay, so I don't think this is going to be that bad. Volume then is going to be 4 times, and here we go. Let's put a 1 in there, where we're going to get a 1 minus 1/3 times 1 cubed is 1/3. I really should put parentheses around that from the 1, and then minus, and what happens when we put 0 into any expanded polynomial? You're definitely going to end up with 0 there. So, not that bad. The 1 minus 1/3 is a 2/3, and the 2/3 times 4 is going to give me 8/3 for our final answer. Because it's volume, I'll put cubic units at the end, and that is our answer, guys, for problem 9 in section 6.2.